Morning friends, today I'll tell you some questions related to TMA. Let's understand what's the pros and cons of TNA. So on the upside, TMA reduces the system noise, improves uplink sensitivity and leads to longer UE battery life. On the downside, TMA imposes an additional insertion loss, typically 0.5 dB on the downlink and increases the installation and maintenance complexity also. The second question is the TMA gain, which is 12 dB. However, the effective gain comes from noise figure reduction, and the gain is closer or equivalent to the feeder loss. Then the question may come the TMA inserted at the top near the antenna. Why not in the bottom near the BTS? So answer is based on a freeze equation. Having a TMA near the BTS will have top jumper and main feeder losses, noise figures cascaded in the TMA. TMA will not be able to help suppress the losses. That's why we install the TMA in the tower top. And then the next question would be in the UMTS, what is the chip rate? Normally it is asked. The chip rate is 3.84 megahertz chips per second. What is the processing gain? So processing gain depends on it's the ratio of chip rate over the data bit rates, usually represented in decibels. So for example, a 3.84 megahertz chip rate and 12.2 kbps data. So the processing gain is 10 into log of 3.84 megahertz divided by 12.2 kbps. That will be equal to 25 dB. So 25 dB is the processing gain for the 12.2 K data. Then now, what are the processing gains of CS and PS services? So for CS 12.2, like we have already discussed, 25 dB. PS64 is 18 dB. For PS128, it's 15 dB. And PS384 10 dB, and for HSTPA it's 2 dB only. How to calculate maximum number of users in a cell? So that's quite a complex question, and it's mostly asked to a little bit more senior guys like the SMEs or something. So to calculate the maximum number of users on a cell, we need to know the chip rate. We already know 3.84 chips per second. We have to know EV and requirements, assuming 3 dB for CS, let's say 12.2K. Then cell to other cell to in cell interference ratio also we can assume 60%. Then we have to consider user data rate, assuming 12.2 kbps, let's say for CS 12.2K. Loading factors also we have to take into account. Let's assume 50% of loading factor. So after that, take let's say 12.2 as an example. So maximum users would be total W by I'll tell you the formula, W by ECN naught into 1 plus I into R. Okay, so I can say the maximum number of users could be hardly limited by OVSF code space. So taking 12.2K for example, CS 2.2K beyond needs one spreading factor 128 code. Then total available codes will be 128 number of OVSF codes minus the formula like 2 into whatever it is. So that will come around 124. So there's a little bit mathematical formula available which I cannot explain here. So that I'll differently discuss in a different session. So for 12.2K, if we are taking into account and we are taking into account the spreading factor 128 codes. So soft handover factor also, let's take soft handover factor of 1.8, loading factor of 50%. So it would be around 34 users per cell. So in the total site it will be 34 into 3. So 102 number of users per node B. So 34 users per cell. So that's how you calculate the number of users per cell. Then the important question is EBNO. So what is EBNO actually? By definition, if we go, EBNO is energy bit over total noise density, total energy per bit divided by noise density. That's the ratio of energy per information bit to power spectral density of interference and noise total. After despreading, EBNO equal to processing gain plus SIR, signal to interference ratio. So that's the formula, EBNO equal to processing gain plus the signal to interference ratio. For example, EBNO is 5 dB and the processing gain, let's say 25 dB for 12.2K voice. Then the SIR would be around minus 20 dB or better. So that's how we calculate EBNO. What is the EBNO targets in your design? So that is a very interesting question. So EBNO targets are dependent on the service, like you're using 12.2K or 384 or HSTP. What kind of services you're using, that depends on kind of services you use. On the uplink, typically CS in the CS services 5 to 6 dB and PS 3 to 4 dB. Minus you have to calculate on the uplink side total CS, let's say 5 to 6 dB and PS 3 to 4 dB, minus PS about 2 dB power. That means if you compare the CS and PS services, around 2 dB difference you'll find, because in CS you calculate differently, because the noise and interference is different. It is less sensitive than the PS services. In PS you need to have better signal and better signal quality, and ECI and RSCP should be very good when talking about PS services rather than CS services. On the downlink side, typically CS are 6 to 7 dB, EBNO targets, and PS is 5 to 6 dB. So around 1 dB difference. So in the uplink, at least 2 dB lower, because CS is 5 to 6 dB, we take EBNO targets, and CS 3 to 4 dB. In the downlink side, we take 6 to 7 dB in CS services and 5 to 6 dB for PS services. Around 1 dB difference. So 1 to 2 dB difference overly in uplink and downlink when we talk about EBNO targets. Then why EBNO requirement lower for PS than CS? As I already told you, PS has a better error correction typically, and can utilize retransmission, therefore it can afford to lower EBNO. CS is real time, cannot tolerate a delay, so it needs a higher EBNO to maintain a stronger RF link, like I've already discussed. So that's all for today. In the next session we'll have some more interesting questions. Thank you so much for watching. Take care. Bye bye.